Week 5, office hours, 129 questions. I'm going to need help getting through these, so we're going to look at some 4.1 questions. I did some of these on Monday, but I'm always happy to do them again because I believe repetition is essential to learning material. So we'll go through these again, and we'll see what we come up with. Number 2, 7, 9, and 24, and then we'll hop over to 4.2. We've got some concept questions that we'll address as we go through these problems. We'll just mention where the concepts come in. The concepts we need to address are two different things. It's this whole flipping between weak acid and weak base, why I'm doing that in lecture and stuff like that. And then just midpoint calculations, which we'll talk about with 4.2 number 5. But we'll just start with 4.1 number 2. This one, and it's 4.1 number 2, 3, and 4, I believe, are all kind of along the same lines. And I didn't really do any examples of this in class because to me, I look at these problems and I'm like, it's Chem 127. Now, there's some new ideas on top of that, but essentially what we're looking at is we are looking at barium hydroxide reacting with HCl, which is going to form barium chloride and H2O. I didn't put my states in there, but we end up with a 2-to-1 ratio on this, 2 HCl's for every barium hydroxide. And now we just kind of go through the stoichiometry. Since we have a strong base and a strong acid, we don't have any equilibrium to worry about, which is part of what makes this a Chem 127 question for me. It's just really doing the stoichiometry until it asks what the pH is, and that's a little 128, 129-ish. So I can just look at this as a stoichiometry problem, and if you can go ahead and tell me what numbers you have, we can get started.
So 19.08 milliliters of 0.220 molars barium hydroxide.
Okay.
And then the other one is 38 milliliters and 0.250 molars.
For HCl?
Yeah.
Okay, so we go ahead, we're going to calculate our numbers for this, and it's asking what the pH of the solution is once these two things mix.
Right.
So we go through our kind of consideration of like what's in the beaker, what reaction can happen, what equilibrium can occur. In the beaker, barium hydroxide and hydrochloric acid, the reaction that can happen is strong acid, strong base reaction. Equilibrium after that, strong acids, strong bases, we're not going to see any significant equilibrium. Right? If we look at barium chloride, this would be like Ba2 plus and 2Cl minus. And if I tried to look at the equilibrium of Cl minus in water, if you tried to form any HCl, that's a strong acid. It's just going to completely redissolve. So we're not going to see any equilibrium, and the same thing happens with barium. If we try to form barium hydroxide as a strong base, it just disassociates again. So we don't have any equilibrium in this case, and so the whole use the Ka values was recognizing that these are strong acids and strong bases. I'm going to convert these to millimoles, right, since we're doing stoichiometry. We're going to need everything in moles or millimoles to do our chemical reaction. So I'm going to take my, wrong numbers, 19.08 times 0.22 gives me 4.198, I'm rounding a little bit, millimoles. Do the same thing over here, 38 times 0.25 gives me 9.5 millimoles. We have to be careful, right? So this is my start. When we do our reaction here, I've had several students having trouble with identifying the limiting reactant. There's 3 different ways we go about it. The fourth is you get good at those 3 ways so you can just do it in your head. So usually people just pick the smaller number and forget to take the mole ratio into account. So one of the ways you can do it is you can just guess and check. If you use this one and then you get a negative number at your end step, at your excess, you picked the wrong thing, go do it again with the other one. Or you made some other mistake, but you've made a mistake someplace. You can also do amount of water that's going to, you can do moles of product. I like doing it the moles of reaction way. This one, because I'm feeling a little time crunched, I'm just going to figure it out in my head. The way I figure it out in my head is I say, look, according to this chemical reaction, I need twice as much HCl as barium hydroxide. If I take 4.2 and double it, I get 8.4. 8.4 is smaller than that. So just by doing a little quick mental math, I can do that with 2-to-1 ratios. I mess up if it's 3-to-2s. I always have to go do it on the side if it's a 3-to-2 ratio. But just with a little mental math, I can recognize that barium hydroxide is going to be my limiting reaction. Limiting reactant, minus 4.198 minus 4.198 plus 4.198, even though we don't really care about the products over there. Give myself a little more space over here. Mole ratio here is going to be 1-to-1. Mole ratio here is going to be 2-to-1. Right, so the coefficient on bottom of the mole ratio is the limiting reactance coefficient. So 1's on bottom because barium's has a coefficient of 1. The number on top is the coefficient of whichever column we're in, whatever material we're thinking about. So for barium, it's a coefficient. For barium hydroxide, the coefficient is 1, so we end up with a 1-to-1 ratio. Here it's HCl, has a coefficient of 2, so we end up with a 2-to-1 ratio. Essentially saying, when this reaction occurs, twice as much HCl is used up as barium, which is why we end up with a 2-to-1 ratio. At my excess step, 0, limiting reactant runs out. Technically approximate 0, but for this one, that approximation is really good because we've got strong acid, strong base. There's no equilibrium going on, no measurable equilibrium. Then we go ahead and calculate this. Is this good so far? Stoichiometry is okay?
I think I know what you're going to do next. I think I just messed up on the stoichiometry part.
Oh, okay. So we do 9.5 minus 4. Oh, that's not right. 4.198 times 2. And we get a kind of small number. Is that right? Did I make a typo? No, that should be right. We get 1.104 millimoles left over. Right, and then at this point, this is our amount of H plus in solution.
Yeah, and then you take the negative. You take the negative log of that directly.
You got to do one more step before it.
Let's put it into hydronium.
And before that, you could do that, but this 1-to-1 ratio for HCl to H plus, so that's fine. But do you take the negative log of moles?
Yeah.
Do you take the negative log of millimoles?
No, you don't.
You take the negative log of?
The molarity.
Yeah. So we have to take this 1. Oh, good grief. You have to take the 1.104 millimoles divided by the total volume, which is going to be that 19.08 plus 38 milliliters on bottom. Notice the milli cancels out, and that will get us our concentration. Divided by quantity 19.08 plus 38. That gets us a concentration of 0.01934. Molarity, we can just call it 10193 with the way I've been rounding. Take the log of that, negative log of that. And you should get like 1.71. .1 has closed, but the repeat for practice is open. I just opened
I feel like
it.
the thing is I was getting something similar last night.
Similar, so these pH questions, we have to be really careful, and actually dropping that 4 there was probably a mistake of mine. Let me check something. Not a big mistake. We have to be careful with our rounding in these problems. Because when you're doing logs of things, more importantly, when you're doing 10 to the power of something, little rounding errors can throw numbers off a lot. So the pH numbers, most of the values that I check in LabPal I do a plus or minus 3% allowance. For pH, I do a plus or minus 0.03 allowance. So not a percentage, but like an actual range. Because little rounding mistakes can make your numbers throw off in really big ways.
Okay, I get this.
Yeah, and then how it changes for number 2 is I think both things run out, so you got to look at the water equilibrium. And then number 3 is the barium or number 4 is barium hydroxide is excess, and people forget to split the barium hydroxide into hydroxide ions. Question.
So if I wanted to like, is there any way I could use the Ka to also get the same concentration of hydrogen?
In this case, the Ka for HCl is like 10,000, 100, like 10,000, 30,000.
Yeah.
So we're not going to have any equilibrium that we would do in this situation, right? The Ka.
Like if I used it, could I still end up with the same answer? Because I could find like the concentration of like I don't know. I don't know what the base would be here.
Right. So it gets you would. We're just going to do the chemical reaction first, and it's going to go to completion.
Yeah. Okay.
And then you're going to have no equilibrium going backwards. Your X is going to be like so small you can't even measure it.
But I also have a question on like, I know there's like strong base and strong acid in this situation.
Yeah.
But when there's like weak acid and stuff like that, that's when
Then,
you equilibrium. But
yeah.
But does that, it also just, that just makes more sense because like you can see the base in the product side when that happens, right?
Yeah.
Why is that? Why is it?
So it has to do with how these chemical compounds interact with each other and interact with water. This kind of gets to the weak acid versus weak base thing a little bit. You know, and it's all about the energy, right? And this is where I could do the class differently and have us talk about Gibbs free energy a lot more often, right? Because there's all of these chemical reactions have some energetic drive. There's some energy in the association of water molecules around them, bonds being formed, bonds being broken. There's also some energetic interaction of how the molecules are able to rearrange, the entropy and the enthalpy. Those two ideas get put together, and we're kind of skipping all that thinking and just saying there's a K value that tells us how much this happens. So the K value becomes, that equilibrium constant becomes our shortcut for talking about how much this thing goes forward and backwards and where that equilibrium energy lies for keeping the products and reactants in some energetic balance. Now, for a strong acid, strong base, that energetic balance is all products.
Yeah.
All products.
Yeah.
There's like 99.9999999999999% products. The amount of like reverse equilibrium to form some HCl left in solution, it's just not gonna happen.
Is barium chloride a solid?
Barium chloride, we could check the KSP for it. If memory serves, it's pretty soluble.
Yeah.
So all the barium chloride, yeah, that says I put AQ because I'm pretty sure it's soluble.
Does it? But if it,
but we could double check. Let me see. Where's an equation sheet? Is barium chloride on there? Barium chloride is not on there, but our equation sheet is not, it doesn't have everything on it. So we can do a quick search. I'm just curious. Barium chloride. Ooh, interesting. It's got a funny crystal structure. I was talking about that in my other class. Density, solubility is like 30, 40 grams per 100 milliliters. So
is that big?
Yeah.
Oh, okay.
Yeah, it's crazy soluble. I thought it was, and I just wanted to make sure I wasn't. Because there's some chloride exceptions, I wanted to make sure I wasn't messing them up. Yeah, so it's super soluble.
Okay. I only asked that because if it was solvent, it would make more sense to me that it wouldn't want to go backwards. But water is very stable and it wouldn't want to split to go back to like
so we could, so this is an acid-base reaction. And, in 127, we learn about acid-base, precipitation, and redox. We could do an acid-base reaction that also has a precipitate.
Yeah.
Right?
Yeah.
Now, they don't have to be like individual things. So we could do more complicated situations where it's like I add these two acids together, I form a precipitate, now I have to do a precipitation equilibrium or solubility equilibrium on top of my acid-base equilibrium. We'll look at how we could deal with that after we finish the acid-base section, dealing with multiple weak equilibrium. And you're running into that in lab some.
Yeah.
There's labs where you are like specifically using not sulfuric acid, because sulfuric acid would have created a precipitate with something else. And there's situations where you're specifically not using nitric acid, because nitric acid would have done a redox reaction with something. Right? So there's cases where it's like, oh, there's cases where you don't use hydrochloric acid because you would accidentally create a precipitate with the chloride ions. So there's places in the lab, if you've ever looked at the lab and been like, why are we using this acid this time? Rather than just being like, this is the acid it told me to use. It's like, oh, there's all kinds of side reactions if we used HCl. And we want to avoid those so we don't have like 3 different like competing reactions happening at once that we're trying to piece apart.
Okay.
So,
yeah.
But we could deal with it, but if we can avoid it, that's better.
Yeah, totally.
Okay, so that was number 2. Is number 7 the graphs one?
Yeah.
Okay, let's look at number 7 real quick. I like that one. I'm going to try to do it better than I did yesterday. And there's just 2 kind of competing, there's really in most of this problem, there's really 3 ideas that we have to keep in mind. I'm going to try to draw 3 graphs. I'm going to try to draw them uniformly this time. Oh, that's so much better than yesterday. Okay, so one of our graphs does something like this. One of our graphs does something like this. And then one of our graphs does something like this. I'm just going to do those 3. I know there's more than that, but these are the only ones I care about. Right? So each of these is a weak acid. We can mark where the equivalence point is. That's the equivalence point. That's the equivalence point. That's first equivalence point, second equivalence point. And then we can say, okay, so what's going on here? What's the first question?
Which curve corresponds to the sample with the highest number of moles of analyte?
So moles of analyte. Notice on this curve, there's nothing like that. The axis is the moles of titrant. So there's nothing on the curves that directly tell us moles of analyte. But I marked a particular point because we know that there's a place where the moles of titrant is equal to the moles of analyte.
Equilibrium?
Not equilibrium.
Equal something.
Equivalence point.
Yeah.
It turns out along this curve, every point on this curve is at equilibrium. Right? Because we add stuff in and it comes to equilibrium before we measure the pH. We always measure pH at equilibrium.
Yeah.
So every pH measurement we make along the curve is some equilibrium. But there's the equivalence point where the moles of our titrant are equal to the moles of our analyte reacted. So all I have to do for which one has more moles is say which one has the equivalence point further out. So I've got one here, a little bit shorter, one even shorter. This one has 2 because there's 2 equivalents being reacted. But this one has the first equivalence furthest out, so it's going to be this one where the equivalence point is furthest over. Takes the most moles of titrant to get to the equivalence point. Means that one has the most moles of analyte.
Okay. Okay, because they're the same thing. They're saying the same thing.
Yeah. At the equivalence point, they're saying the same thing.
Yeah. Okay.
Okay. Next question.
Which curve corresponds to highest concentration of analyte?
Now, this one is tricky. This one's kind of a silly trick, right? So, right. Less moles to first equiv. So there's our moles, less moles, less moles. How do we get concentration?
Milliliters over moles. I mean, moles over milliliters.
There we go, right? So my hunch on this problem, when I first read this problem, I was like, oh, of course the one with more moles would have more concentration. And then I read the problem again, and I was like, oh. They don't tell us the size of the sample. They tell us that they all have that the titrant being used is the same concentration of titrant in all of them. They tell us that here are the curves. They don't tell us the volume of the sample. I just assumed that if I was setting this up in a laboratory, I'd make it so all the samples were the same volume. But we don't have that information. That's an assumption I'm making. And if I don't make that assumption, I can't tell what's going on.
Yeah, I do that. Oh, so you already gave these tests? Yes, I do that all the time. I have to scratch questions, especially if I decide to.
So right, since the volume's not given, we don't know if the samples are the same size. We can't actually say anything about the concentration in that case.
So, but like, let's say we did know the volume.
I mean, you can, are they all the same volume?
Yeah, like they're all like 10 milliliters.
Then it's going to be more moles divided by 10 versus less moles divided by 10. This number's going to be bigger.
Yeah.
Right? If
Yeah.
we knew that they were all the same size, it's easy. The one with more moles is more volume, more concentration.
Okay. Yeah.
But if their volumes are different between all of them, can't do it that simply. We'd have to calculate the concentration of each one. We'd have to like eyeball what's the volume, calculate the number of moles, and divide the moles by each volume to get the concentrations.
Yeah. Okay. Okay.
Too complicated for a little problem like this. It's just supposed to make us think, do we have volume? If we don't have volume of the sample, we've got volume of titrant, because that's the x-axis, but we don't have the volumes of the samples.
Yeah.
Part C?
Strongest base, but you don't have that curve drawn.
That's the curve I don't have drawn, right? So the strongest base is just going to be the one with the pH that starts the highest, right?
Oh.
A base curve just looks like the opposite of an acid curve. You start at high pH, you go down to low pH.
And then the next one's the strongest acid.
How do we tell strongest acid? This one, ooh.
Oh, so this is just the opposite.
Well, this isn't just, so strongest base was easy because there was only one base. Strongest acid is a little bit tricky because we've got 3 different acids to consider. So what do we use to tell the strength of an acid?
pH. Or Ka.
Ka, right? pH tells us something about it, but Ka. Where on each of these curves can we say something about pH and pKa?
The equivalence point.
The middle point.
Midpoint.
Midpoint.
Midpoint. Right, so that midpoint is going to be where pH equals pKa. Right, and this is one of the things I talked about. That's a big benefit to having pKa lists. What you're going to do in lab next week is you're going to measure the pH of the midpoint to identify the acid. You can measure the pH of the midpoint and say, okay, that's the pKa. That tells me how strong the acid is. I can look at a list of pKa values and approximate possibilities for my acid. So, is a higher pH a stronger or a weaker acid?
A weaker acid.
Higher pH is a weaker acid because a higher pH is less H3O+. So all we have to do is pick which one has the lowest midpoint. That's going to be our strongest acid. This first curve. At least the way I have it drawn. I don't know if your pictures are the same.
It's the second curve, the one that's like that.
Oh, it's the that one has a lower.
Yeah, it has a pH of 7 at the midpoint. Well, that's the midpoint, right?
Oh, we're going to look at the first midpoint.
Oh.
Yeah, so like this first midpoint, right? This first acid is going to be the stronger one.
Okay.
Yeah.
So
not the way I have it drawn. Look at the graphs you have.
But I just mean in like summary, you said the lower the pH, the weaker the acid.
Lower the pH, stronger the acid. Remember, pH is an inverse scale, right? It's negative log. So lower pH, lower pKa, stronger acid.
Okay.
Which is higher H3O+, higher Ka, stronger acid.
Okay.
The negative sign makes them flip.
Got it.
Okay?
Okay, so it's like 4/1 as a fraction of like Ka.
Yeah.
Yeah, so 4, and then negative log would make that look really small, even though it's like way bigger than like 2/1.
Sure. Yeah.
Right?
Yeah.
Okay.
Yeah. I do 1/4 versus 1/2, just because the negative log of positive numbers is kind of a weird thing to do. Of numbers greater than 1.
Okay. Okay, got it.
Okay, and then the part the last part of this problem is saying, what's the dominating species at that point?
Yeah.
Right, so at this point in the titration curve, we're at the equivalence point. What's the only thing left in solution at the equivalence point?
Water.
And so weak acid, strong base titration curve.
So,
Equivalence point has reacted all of the weak acid.
and so it'd be water and a little bit of base.
What kind of base?
Conjugate base.
Yeah. It's going to be that leftover A minus, that conjugate base is going to be dominating at that point. Now, if we go past that point, if we go up here to where the curve is just flattening out, that's where just our excess hydroxide, our excess titrant is going to dominate. But if we're exactly at the equivalence point, that's where we have exactly all of the weak acid and all of the strong base used up, forming conjugate base only. The last one, and I feel a little bit mean for this one, the last one is somewhere in this part of the curve, right?
It's the
Yeah, so
middle
it's like right there. Okay. And you notice for this one, it asks you to input 2 materials, right? And so to talk about this, I'm gonna look at these 2 different regions, right? And I feel the reason I feel a little bit mean is because I haven't done it as an example on the titration curve, but we've definitely defined Ka1 and Ka2. So this area here is that first buffer region where our conjugate system is going to be like H2A going to HA minus plus H3O plus. Right, so in that first area, I'm going to have this generic acid and its generic conjugate base, and there's going to be that kind of combination between the two. In this area, I'm going to have HA minus going to equilibrium with A2 minus plus some H3O plus. Squeezing, that's kind of awkward on the edge there. Fix that a bit. Right, so it's going to be the equilibrium of these 2 compounds that kind of dictates where the pH is. Now, if we're exactly at the midpoint, those 2 compounds are going to be approximately equal to each other. For one side or the other of the midpoint, one will be bigger or smaller than the other. But generally, in the buffer region, remember the definition of the buffer region is we have a weak conjugate pair. A weak acid with its conjugate base, or a weak base with its conjugate acid. And this brings in the weak acid versus weak base situation inside of the buffer range. So the place where we do this flipping, there's 2 places where we do this flipping. It's when we're at the equivalence point, or anytime we're in a buffer region. And the way that I think about this, for the conceptual work that you were asking about earlier, is back to our simple questions. What's in the beaker? Right, so what's in the beaker? If we're in, let's see, I need another color. Too many things on the board at once. If we're at this red spot where we've got A minus in solution, that's the only thing I have in solution. Only A minus, and water, right? Right, all of these always have water around as well. There's only one equilibrium I can consider. Right, so that one equilibrium possible is going to be A minus plus H2O goes to HA plus OH minus. That's the only equilibrium I can consider because that's the only thing I have in the beaker. What if we're at this point? Let's do it for this particular one. if I've got HA minus and H2A in solution, if I've got those two things, I can look at two different possible equilibrium that are going to be directly related to each other. I can look at HA minus plus H2O goes to H2A plus OH minus, or I can look at H2A plus H2O goes to HA minus plus H3O plus. Both of those equilibrium, I should say more carefully, both of those ways we represent the equilibrium are valid. And if we do the calculation of the Ka versus the Kb and the pH versus the pOH, it turns out it's the exact same thing. It's just how we're representing it. Now, in class so far, when we have this choice between the two, we haven't asked any questions that say, what's the pOH? Right? Every question is asking, what's the pH, what's the pH, what's the pH? Because if you can find the pH, you can find the pOH. Like, why ask about both when you can just ask one and relate the two? Since every question is asking for the pH, this one becomes easier to use. Now, the only, I can't write this. Right? The only benefit of doing it that way is that we just save a couple math steps. Right? Those two equilibrium are, the two ways we're representing the equilibrium are just talking about the same thing in two different ways.
So if we wanted to get back to like the question itself, when it says the first predominant chemical species in solution that will determine the pH, it's the first blue dot.
The point it's at on that one is actually the orange bit, if I remember which one it's pointing to on the curve.
Okay. Yeah.
So it's going to be like
at the point indicated. Yeah.
At the point indicated. So we've got, so it's going to be that HA minus and that A2 minus. I need to add a note in there. I think I want to change that to a drop-down menu, or something. Not a drop-down menu because everyone just guesses if I do drop-down menus too often. But a note that says a generic acid can be used as. I usually do a lot more generic acids in class. I've been trying to do real compounds a bit more. I was encouraged by some colleagues.
So would I say HA?
HA minus.
HA minus.
Because you're in that second proton area.
Yeah, and I know that because at the top of the screen it says HNA, and then I'm assuming it's in water.
Uh-huh.
And I only know that one, because I'm so confused about how you concluded that was that variant of that acid at orange, like at that.
Oh, that's the definition of like Ka1, Ka2 that we did like 2 weeks ago.
Yeah, well, yeah, I get that, but I just mean like, is that the definition? It's just the equivalence acid, or like what?
The definition of Ka1 is this chemical equation I have written in blue, where it's the first proton being lost. Ka2 is the second proton being lost.
Yeah, and you just know that it's K2 at that point because it's like
midpoint, too.
It's a midpoint?
Yeah, it's the second midpoint.
Oh, okay. Yeah. See, I didn't put that together.
Right. What's the pH at the second midpoint?
Whatever that is.
pKa2.
Yeah. Oh, yeah.
That's
Okay.
that easy. Right?
Yeah.
What's the pH at the first midpoint?
pKa1.
That's it.
Okay. So just negative log of Ka at that acid. Okay. Okay. Yeah. Just gotta keep
So it turns out, and this is where this class is frustrating but relieving, because it's like all this stuff feels really complicated, and it's like, wait a minute, it's actually just that straightforward. Like once you see those patterns, it's like, okay, I see what's going on. I'd say this weak acid, weak base, this two ways of representing the same equilibrium is the part that students have the hardest time wrapping their heads around. Because they're used to a chemical reaction being the chemical reaction, you have one chemical reaction, and that's it. It's like, well, we can represent with weak acid, weak base, we can represent the equilibrium as the weak acid or as its conjugate base, because the conjugate, like, that's just going back and forth. And they're equivalent to each other with different K values. Because it's the Ka for it going as the acid, the Kb for it going backwards as the base. Okay. Should we look, since we're talking about all this stuff right now, let's go ahead and let's look at number 3 and 5 on 4.2, because I think that's going to be related. And then we'll come back and look at number 9. Like, all of these things, at this point, like, all of these questions are ending up related to each other. Like 9, 3, 5, 24, they're all kind of doing the same stuff. So, but you've been really patient, so I want to figure out what's going on with your midpoint calculation.
It's just what we did it in class, which is where you were just talking about how pKa equals the pH at the midpoint.
Uh-huh.
And so on number 5, it would be the pKa. So it's I don't know if it's easier if you look, but it's like.
Oh, look, give me just a second. I just wanted to do this.
It has a higher
pH
one.
equals
But that,
pK.
if we just
What?
did 9 times hydrogen, we just got the moles of equation.
pH
But it wants to
equals
know
pKa.
moles of
2.
phenolate and the moles of
Right, so
phenolate
we've got this
is
kind of
not
relationship. Let's see what's happening underwards.
Well,
Moles
so
of
there's
phenolate is
this,
acid.
and so when I look up
But
the
he said that at
Ka
the
of
equivalence
nitrous
point,
acid,
the moles
should
of
be right
titrant
here,
and phenolate equal each other.
and then
So that's how you know.
I'm confused
if
on, like, the
this-
difference
basically,
between
if this is
PK
the
and
biggest
Ka.
one.
Ah, okay. So this is a really important thing, and so that I think that's all that's messing you up.
And then that
Right.
equals another one.
Yeah.
Do you know what the P function does?
And that's what keeps on
It's like-
confusing me.
I'll
Is
try
midpoint
to
is the same thing too.
That's rude.
That's like it's like the log
Right.
and the base.
Now, technically, for this one, it's the negative log of the H plus
Yeah.
concentration, but it's the negative log. So pKa
Mm-hmm.
is,
The negative log
that's it.
of the Ka. Okay.
That's
So
it.
I would need to take.
So
So
if
then
you-
how come for in class we didn't change our Kas? Or maybe I just wrote it all down wrong.
Let me see.
Yes. Well, I think we only did number 1 here.
We only
So-
did number 1 on the board. Yeah, that's not.
So it would be, you'd have to take the negative log of it
Yeah,
first, and then,
so it's the next step, pH
Okay,
is pKa. So you have to take the negative log of that, you get 4.74. I just happen to have acetic acid memorized at this point because I've used it.
okay,
like-
thank you.
I get tired of using acetic acid as an example because it's like the only example you can find in so many books, in so many videos. Like 9 times out of 10, if you find a video about weak acids, it's going to be about acetic acid. So that was number 3.
That was number 5.
That was
and then,
number 5.
I think he
Okay.
asked about number 3.
Yeah. So number 3 was just the question, discuss with a classmate.
Oh.
How would so
Yeah, let's discuss.
let's discuss. How would changing the identity of the acid change the midpoint and or the equivalence point? And I think we just kind of went over
I
this.
think we just did, right?
Yeah.
So that's the nice thing. I'm glad I didn't erase this stuff, right? Now, 2 aspects to midpoint, right? The midpoint has an x value and a y value. Does changing the identity of the acid change the x value?
The identity of the acid change the acid. No.
No, right? Because that's the stoichiometry aspect. I would have to change the amount of the acid. Are we putting in more
Yeah.
volume or more concentration? Does changing of the identity change the y value?
Yes.
Right, because that pH equals pKa, so if you
Yeah.
have something with a different pKa, that y value is going to change.
Okay.
So you can imagine having a second curve that kind of does the exact same thing as the first one, where that second curve is a different acid, midpoints in the same spot if I made them the same way, but now that pKa, that y value has changed.
Yeah. Okay, and that makes sense. If I change the Ka and that changed how much the acid dissociation, whatever, now I have more products, because I have more products, when I do the negative log, I get
A
less
different
pH.
value. Yeah.
Okay.
Same type of logic for equivalence point, right? Does your X value change when you change the identity of the acid?
Of what? Of the equivalence point?
Yeah. Right? X value stays the same if the identity of the acid changes. If it's the same number of moles, your X values don't change.
Yeah.
It's like all the examples we did in class. Was that on Monday or was that on Friday? That was on Monday because we had the midterm on Friday.
Yeah.
On Monday we did all those examples. So we
Okay.
had all those examples where it's like 1, 2, and 3 were the same thing
Yeah.
because they were the same number of moles. So the volume to midpoint, volume to equivalence point was the same. pHs at midpoint were different.
Yeah.
pHs at equivalence point were different.
Okay.
Because at the equivalence point, oh, I did erase one thing I need. At the equivalence point, it depends on how well A minus acts like a base, which is going to be like Kw divided by Ka.
Okay.
The weaker acid will have a stronger conjugate base that will send the pH at the equivalence point higher.
Okay. Okay.
So that's the discussion of like what's going on, and it's like I'm glad we did that when I was doing number 7 before I erased these graphs, because
Yeah.
that's kind of the same idea of like, can we interpret what's going on between all of these?
Yeah, I feel like there's like, I know you said it's like easy, like when you think about it,
Yeah,
but
it's not easy
but
yet.
There's a lot of steps you have to go
Yeah,
through
it's
to
not
get
easy yet, right? And that's the whole idea, is that we do this enough that by the time we get to the next midterm, it's like, oh yeah, it's this
No-brainer.
again, right?
Yeah.
Like I will tell you now. I've already told the entire class this, so this isn't news. But I'll say it again as the midterm gets closer. The next midterm, I think I'm gonna do it in week 7. It's like a short turnaround to the next midterm, because the next midterm is only covering titrations and buffers.
Okay.
Right? It's all the titrations and buffer stuff we do. So week 5 and week 6 is titrations and buffers. A little bit into week 7, a little bit of week 4 is all of this stuff as well, like titrations and buffers. And I wanted to make a midterm that's only titrations and buffers. Guess what's going to be on your final? I've already told you. Titrations and buffers will be on the final. I feel like if you can't do a buffer problem by the final, you shouldn't be able to pass the class. Like if I had my way, I'd have a buffer problem on the final that is worth plus 10 points and negative 100 points. Like if you get it right, you get 10 points, but if you get it wrong, minus 100. Apparently that upsets students, so I can't do that.
I'm really glad. it's not.
Technically, I don't think anyone in the chemistry department or the university would stop me. So I made it like SAT style.
I mean,
But
you
It's a
have a
headache.
riot on your hands.
yeah, probably.
Yeah.
So I just tell everyone, I'm like, please get it right.
And then a buffer problem would look like this.
We haven't gotten to buffers yet.
Got it. This
It's
is
going to be
titration.
related, right? We know where the buffer regions are, so it's going to be calculations in those regions, which technically we've already done,
Equilibrium.
but we haven't done it in the context of calling it a buffer and using the terminology of a buffer.
Okay.
Whew. Okay. Number 9 from 4.1.
Yep.
Which I think is actually a buffer calculation.
Let's
Well,
go.
it's a within the buffer range calculation. It's weak acid conjugate base calculation. I think that's number 9. I'm gonna erase all of this, I think. So we did this. Cool. We're doing great. Goodbye, nice graphs. If you look at the video that I posted from yesterday, my graphs were like, they weren't bad, but if I don't move over when I'm drawing lines, like one of the lines is like at an angle, and so the curve, I'm like, how do you compare it when the curve is like sloping off to a side? In any case. Okay, do me a favor, Reed, what's number 9 got us doing?
Consider 20 milliliters of solution of 0.37 molar hydroxylamine.
Hydroxylamine. Oh yeah, 20 milliliters of 0.37 molar.
Hydroxylamine mixed with different volumes of 0.15 molar hydrogen bromide.
Hydrobromic acid.
Hydrobromic acid.
Yeah.
Okay, so the first one is what's the pH of the original solution before adding acid?
Okay. Right, so the pH at the volume of strong acid in this case, equals 0 milliliters. Now, have we done any weak base calculations in class yet?
No.
Can we do them because they're exactly the same as weak acid? Probably, let's see. So first thing we're doing nothing added, so all I've got is this HONH2 in solution. So I go HONH2 with water. It's going to have some equilibrium to have HONH3 plus OH minus. That's going to have a KB associated with it.
Wait. HONH2 is a base.
Yeah.
Okay. I don't know.
So
I looked on the sheet and it said it had a Ka, or maybe it had a KB.
Yeah,
it has a KB.
Oh, okay. I just misread it.
Yeah.
it's 1 point.
There we go.
5 times 10 to the base.
Yeah.
Right, and so the fact that it has a KB tells us, oh, this thing is going to behave like a base, and we got that 1.8. Thank you for that. 1.8 times 10 to the minus 7. Whoa, that's not how you write minus 7. Minus 7. So notice 1.8 times 10 to the minus 7. I can have my 0.37 molarity. So in this situation, nothing's being added. There's no stoichiometry. We go to our typical questions. What's in the beaker? Hydroxylamine. What chemical reaction could happen? Not really anything. I've only got one thing in the beaker. What equilibrium can occur? This equilibrium can occur. 0, 0. Minus x plus x plus x. 0.37, I'll just call it approximately 0.37. That's pretty small. I'm going to use the x small approximation. X and x. And then I'm going to have 1.8 times 10 to the minus 7 is equal to x squared over 0.37. X in that case is going to be like, that was slow enough, right?
Yeah.
Because we're really good at these now. 1.8 times 10 to the minus 7 times 0.37. Whoa, not squared, square root. We get 8.16 times 10 to the minus 4. I take the negative log of that, and I get 3.08, I'll call it 3.09, 3.088. What's the important tricky thing that I didn't write down yet? The part that messes people up. They do all of that and they're like, cool, pH 3.09. When we're doing the weak base, that's the pOH.
Oh shit. Yeah.
Right?
Yeah.
And so we just lose track of it because once we start jamming through the ice table, we're just like, oh yeah, we've done this all the time. We solve for x, taking the negative log of x. That's the answer. It's like, oh, hold on, right? And that's where sometime in week 3 when we were first doing weak acid calculations, I said always stop and slow down. Ask yourself, what is the x? What's the x I just solved for? Because every time we set up an equilibrium table, we're solving for x. And the x does not mean the same thing. Most of the times the x doesn't mean the same thing. So we always got to slow down and check and be like, okay, what is x this time?
What just confuses me though is okay, no. Sorry. I was gonna say if x is the same thing as HONH3 concentration, then that would be the proton concentration. But that's not pH. pH is just acid versus base.
Yeah.
I always okay.
Yeah. So we got to do 14 minus 3.09, and we get a pH of 10.91. The other thing is a pH of 3, when you put a base into solution, should also be a red flag to you. Right? You should see that and be like, well, I was expecting a base to make a basic pH. pH above 7. Yes, forgot your 14 minus. So that's 1. Now, number 2 is a little bit more involved. I'm going to erase this and we're going to do number 2 because I'm going to need all of the space I can get. Number 2.
What volume, what the acid is needed to add the the same number of moles let me try that again. What number of acids is needed to add the same number of moles of acid as base?
Okay, so we want to have equal moles.
Yeah.
So that's kind of a weird way to say what volume to get to the equivalence point. So we go ahead and we say, okay, well, how many moles do I have to start with? I'm going to have 20 milliliters times 0.37 molarity. That's going to get me my number of millimoles. 20 times 0.37, 7.4. Yeah, I could have gotten that, right? 21 times a third should have been about 0.7. 7.4 millimoles. Then I do my 7.4 millimoles times 1 milliliter per 0.15 millimoles. Right, that's my concentration of HBr. Divided by 0.15. 49.33 milliliters. Then what's it ask?
And then enter the formula of chemical species predominantly present after adding volume of acid in part B.
And then?
That will determine the pH of the solution.
Okay, so we've got our volume. Now, what's number 4?
What is the pH of the number? What is the pH when the number of moles of acid added is equal to the moles of base? So I guess equivalence point.
Yeah. And I want to do these. I want to do these two at the same time because I find figuring out what the dominant chemical is easier when I write down the chemical reaction and think, okay, well, what's left in solution to have an equilibrium? So I'm going to do these both at the same time. I'm adding a strong acid to a weak base, so I got to do a chemical reaction. I'm going to have, okay, no, I'm not going to do it that way. We're going to have our HONH2 plus HBr. That's going to go to HONH3 plus Br minus floating around the solution, right? I've got this proton being donated across. Proton donor, proton acceptor. Br minus doesn't matter. I could write this as H3O plus Br minus, and Br minus becomes a spectator ion. I do my stoichiometry. I just erased my number of millimoles. Why did I do that? So we've got our 7.4. I just remembered it. We got 7.4 millimoles there. We got 7.4 millimoles there. We got zeros there. Don't really care about that one. My reaction, since they're equal amounts, I could consider either one as limiting reactant. 7.4, 7.4, plus 7.4. And then at my excess step, I've got 0, 0, 7.4. So after doing the stoichiometry, I can say, okay, both things run to approximately 0, really close to 0, approximately 0, because both things are limiting reactants. At the end of all this, because I'm at the equivalence point, I only have conjugate acid present. So what's going to be the dominant chemical for the pH?
Conjugate acid.
Conjugate acid. It's the only thing that's present to do anything. Then we can say, okay, well, what does that conjugate acid do and do the equilibrium? Now, we only have conjugate acid. This is a situation where I don't get to choose. I've only got conjugate acid in solution. I have to look at the equilibrium of conjugate acid. It's only when we're in that buffer range, that buffer region where we have the conjugate pair, where we get to make choices, because there's two things there. One thing there, I've got no choice. It's going to donate protons to water acting as an acid. I'm going to have, I got to be careful, 7.4 divided by?
The 20 plus.
Yeah, total volume.
Whatever
69.33. 0, 0, minus x plus x plus x. I ran out of space. This is going to be approximately equal to 7.4 divided by 69.33. 0.1067. 0.107 is close enough. X. Didn't give myself enough space for the problem, so I'll move over here and I will say Ka equals x squared over 0.107. And I can get Ka by doing the Kb value. Oh, sorry, it's like Kw divided by the Kb value. And it looks, here's the nice thing about the equivalence point calculations that I don't know if we've done enough to notice this yet. At least we haven't done enough in class. The equivalence point just looks like a weak base in water or a weak acid in water. Right? This is exactly like, we only have weak acid in water. It's a weak acid calculation. We end up with x squared over concentration equals Ka. When we do it for the equivalence point of a weak base, it's x squared over initial concentration equals Kb. That x is OH minus instead of H plus, but same calculation.
I have a question for just like going back.
Well, let me make sure. Good?
Yep.
Good?
In black, that is what you're talking about, it's a weak acid in water.
Right, because
And
all we
start off
had,
with the blue.
yeah, we
Right,
started
just
with the blue.
simplify.
The blue is the stoichiometry.
Yeah.
Once we did the stoichiometry, we said, okay, well, what's left, right? That's the chemical reaction happening. After that chemical reaction happened, we said, okay, well, what equilibrium can happen?
And conjugate acids are only left.
Only conjugate acid
So then
is
it just
left.
turns into like what we've been doing.
So it just turns into an equilibrium of a conjugate acid and waters.
Okay, sounds good.
Cool. Now your question. Oh, are you good?
Yeah.
Okay. Now your question.
I don't even know if I don't even know what to ask. Like,
Well, so I'll tell you the same thing I told office hours yesterday.
yeah.
Things get easier now. Like if you're like this is making sense to me, so like I don't know if I have a question. Is that how you're feeling, or is it like?
No, it's like you did it on the board. You found
Yeah.
it's for B. It was the volume of things to equal it, like
Uh-huh.
equilibrium. I was just wondering if you could do it in a different way, where you find the concentration of HBr, and then convert that using the Kb. You find the concentration of HBr, and then convert HBr into like moles.
Oh,
Good.
that's what we're doing next. Like we're going to be
Oh.
learning that Wednesday and Friday. So
Okay.
I think the question you're asking is, can we do this whole problem backwards?
Can we just do it? Could we do it a different way?
Since we're given the concentration of HBr, not really.
Oh, okay, yeah.
Right? So the place where we can do this problem differently is when we are told what the pH is, and we're asked how much it takes to get to that pH.
Okay.
Right? But it's the same problem, but it's like once we get comfortable, like on Wednesday, we'll get to the point where we're like, oh, we finally feel good doing these problems forward.
Yeah.
And the next slide will be, let's do it backwards.
Great.
Just to, like once we're comfortable with this forward, and it turns out doing it backwards is usually very useful. It's the more useful version of it because you're trying to make something to get to a particular pH.
Yeah.
So the question becomes, well, how do I make that particular pH, right? Biological systems need to be held in a buffer at a particular pH. How do I make that buffer? Physiological systems, environmental systems, right? Your brain has a different buffer than your blood has a different buffer than your stomach acid, right? They're all buffer systems. And your body's just like moving these buffer systems around and keeping them in balance.
Yeah. Yeah. Okay. That's cool. Okay.
Yeah. So that's what we're doing. I'm going to go ahead. Are there other pressing questions?
There was
Number 24. Okay, we'll do number 24 before I stop recording. What is number 24?
let's see, strong base, weak acid before equivalent. So it's 86.98 milliliters of 0.998 molar generic monoprotic weak acid.
What was that molarity?
0.998. And then it was with a Ka of 9.14 times 10 to the negative 5.
10 to the negative
5.
5. Okay, I thought you said 9 for a moment. I was like, that's a weak acid.
Yeah.
Okay.
And then is titrated with 1.01 molar sodium hydroxide.
How much?
That's, what is the pH after 27.45 milliliters of strong base has been added?
Okay, so we look at this and we say, okay, what's going to happen? We got a weak acid. We got a strong base. Chemical reaction. Right? So we're going to have some chemical reaction happen. After the chemical reaction happens, since the prompt tells us we're before the equivalence point, we're going to be probably in the buffer range. We're going to have a conjugate system. Let's take a look at that. Okay, so starting with step 1, we're going to do the stoich. Figure out how much we have. It's going to be HA plus OH minus goes to, and this one I could probably put as a straightforward arrow because it's a strong acid, so it's just going to go forward. This is going to go to A minus plus H2O. Aqueous, 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 liquid. My starting amounts are going to be 0.998 times 86.98. This is 86.81 millimoles. For the hydroxide is 0.101 times 27.45. Oh, did I mess up someplace? No, that looks right. No, that's right. That's just a really weird number. 2.77 millimoles. 0, 0. Huh. These are randomized numbers that might mess things up. We'll see how it goes. So, why am I already worried?
There's not a lot of strong base.
There's not a lot of strong base, and the first thing I do usually when we're doing titration problems, the first thing I do is I think about where am I on my titration curve? With this strong amount, with this small amount of strong base, I'm worried we're down here in the curvy bit where I don't like to calculate things because extra small approximations fail. I don't know if we're actually in that area. I could do a quick check. I think we're going to be in a little trouble. Let's do it and see what happens.
I've got different numbers.
Yeah, so other numbers might work better. I think your random numbers are just kind of like...
I got like a pH of 4 at the end, like 4.3.
That makes sense to me.
Yeah.
That makes me think that. Let me double check my punching stuff.
But this is.
Wait, was it 0.101 or 1.01?
Oh, sorry, I said 1.01.
Oh, that's where it's messed up. Okay. Whew.
I was like, this.
Okay.
I don't remember it being that small.
Okay, 27. Okay. So you notice, like, my concern. So here, I just did a great demonstration of expectation thinking for you, right? I didn't do that on purpose. It was because I made a typo. But because I know how the titration curves work, and I know generally where we are in the curve, I had a hunch that there was something wrong. Because the problem that you had with the numbers that I thought you had, because I was off by a factor of 10 on the concentration, we were in a place where the I knew the extra-small approximation was going to fail in our equilibrium table. And so I was like really worried something was going to go wrong. With this number of 27.7, we're going to be like up here, and we're going to be fine. And I'm going to expect a pH somewhere close to the pKa, right? We know the pKa is the midpoint. The midpoint would be like half of this. That would be like 43. So we're like not far from the midpoint. We're halfway away from the we're like halfway between the beginning and the midpoint. So we're gonna be like there. I would guess you'd get a pH. Let me get the pKa real quick. 9.14 times 10 to the minus 5. Take the negative log. So the pKa, the pH at the midpoint is 4.039. With this, I would guess that you get like 3.8.
Okay. I mean, I might have done it wrong. It was one of the graded questions. So
Okay.
It doesn't show you if you were right or wrong.
No, I'll release that feedback in a couple days. What pH did you get?
I got 4.3.
Yeah, that seems wrong to me.
Probably.
That seems like that's what I would expect on the other side of the midpoint.
Okay.
Right? So instead of being 27, if this was like 67, then I would expect something over there.
Okay.
Let's go ahead, let's do the calculation together and see where that went wrong. But yeah, curve thinking, the titration curve thinking is part of how I make sure, like, if you get a titration curve thinking, you can ballpark most of your answers and be right most of the time. Like, I'm willing to bet you the answer ends up being 3.8-ish, just from the way that I know titration curves. Let's see, 4.03, 3.03, what's halfway? Maybe 3.6, if I actually like do a quick check. But let's go ahead and see what we get. Going through the whole thing. Hydroxide is a 1-to-1 ratio, so smaller numbers limiting, minus 27.7, minus 20, I almost put 27.7, plus 27.7, this is 27.7, this is 0, this is 86.81 minus 27.7, 59.11. So here's how I know we're going to have, I'm at another point where I'm like, cool, the pH is going to be lower than the pKa because I've got more acid than conjugate base.
Right.
I'm not at that midpoint where it's half-half yet. But let's go ahead, let's do the equilibrium table to tell for sure. Which equilibrium should I do? The weak acid equilibrium. Is there another choice I could make?
No.
Oh, you have weak base.
Doesn't it split into two?
I could
Well, you
do either one.
Just do the
right?
OH one, the acid.
So
That we normally do?
doing it in terms of the acid or doing it in terms of the conjugate base is looking at the same thing from two different perspectives.
Yeah.
Right? So we're looking at the same thing from two different perspectives. We pick the perspective that's going to be quicker, easier math, stuff like that, right?
Yeah.
You can do perspective, you can pick different perspectives for different reasons. We're going to do the one with easier math. So we're going to have our equilibrium be HA plus H2O goes to A minus plus H3O plus. And we like this one because it gets us the H3O plus, which is going to get us pH. My HA, I'm going to do a little cheeky thing here. 59.11 divided by volume total. Right? And I could calculate the volume total, but I'm going to do a little tricky thing that I really like. That's going to be really useful in the future. I'll do it in class probably on Wednesday or Friday, and we'll be like, wow, that's great. 27.7 divided by volume total and 0. That's my initial, right? Moles, millimoles divided by milliliters gets us molarity. My change is minus x plus x plus x. My equilibrium is approximately 59.11 divided by volume total. My A minus is approximately 27.7 divided by volume total. My x is just x. Now, when I plug this into the Ka expression, I'm going to have Ka is equal to concentration of A minus divided by concentration of HA times the concentration of H3O plus. Yeah? That will get me 9.14 times 10 to the minus 5 is equal to 27.7 divided by volume total divided by 59.11 divided by volume total.
And those volumes just cancel out.
Yeah. If we have a ratio of concentrations in the same total volume, it's the same as a ratio of moles.
Okay.
So it turns out, and this is I'm doing something early for all of you. Like we're gonna do this in class on Wednesday and Friday. But it turns out in like 2 more simplifying steps like that, we'll start completely skipping the equilibrium table and just pulling numbers from the end of our stoichiometry. Because the equilibrium always comes out this way. We always end up with the ratio of weak acid to conjugate base solving for pH. So those volume totals always cancels out, and we could technically do a ratio of millimoles and have it be the same as our ratio of concentrations since we're in the same total volume. But at this point now I just solve for my H3O plus, and my guess is if you flip this fraction over, you get 4.3 instead of 3.6.
Yeah.
So, but let's finish it off. 9.14 times 10 to the minus 5 times 59.11 divided by 27.7. That gets me, I didn't give myself enough space, so I'll just do it over here. That gives me my H3O plus is equal to 1.95 times 10 to the minus 4, 1.95 times 10 to the minus 4. And that gets me my pH is the negative log of that, 3.71. Not far off from my 3.638 guess, but obviously I would if I put 3.6 by eyeballing it, I'd technically be wrong. I'm off by a 0.1. Being off by 0.1 doesn't seem like a big deal until you realize it's logs and tens.
My base moles was bigger than my weak acid.
So you should end up with a pH slightly bigger than your midpoint pH.
Okay, I got like 4. But
But you had a different Ka value as well?
yeah.
Yeah, that's fine.
Yeah.
What was your Ka value?
I did it wrong. It's incorrect. I don't know.
Oh. What's your Ka value?
Ka value is 8.72 times 10 to the negative 5.
You got a pH of 4?
Like 3.99.
See, I would expect you to get something like 4.2 just from eyeballing the curve.
I probably just did moles wrong.
Do you have your work any place for it?
Yeah.
May I take a look?
Yeah.
Let's take a look. Okay, I'm going to pause the video while I look over this. Oh, here, I'll just show you all. It's that one? So we're looking at this work, trying to figure out what's going wrong. Okay. Stoichiometry looks fine. Your HA, your A minus, you end up with a little bit more of that than that. You've got your total volume. This looks right. Where'd it go wrong?
In my calculator? No, it's definitely not my calculator.
Just blame the calculator, not
Yeah.
the person pushing the buttons.
Screw this calculator.
Okay, so from the numbers that you
Oh,
have
maybe it's the
here,
total volume.
total volume cancels out, so that's okay,
Oh, yeah.
as long as you didn't divide wrong. 21. Let me just check something else real quick. 89.47 times 0.237. 21, okay. And then 0.254 times 44.59. 11.3, that looks fine. 0.87, good. Times 8.72 times 10 minus 5 divided by 9.87. Huh. Is this on the one that can still be evaluated?
Yeah. This is on the practice one.
Well, that's funny. What went wrong here? Let me check something else real quick. Okay. You know what? See you later. 21.204 minus 11.33, 9.87. What's going on? A sample of generic monoprotic weak acid is titrated with. Let me see if I got a typo someplace. I just found the typo. It's such a silly typo. Have you found the typo?
It's like a door.
Call it more.
Okay, so here, I'm gonna mark it. How do I pick pen color?
Bottom right should be a
Got it.
paintbrush.
Okay. This is just like such a funny typo that like it took me ages to catch. Same typo I think the other person here earlier made.
Yeah.
You did acid over base instead of base over acid in your Ka. You see it?
Wait.
I just circled it in red.
I put 9. Oh,
Right?
Yeah.
You just flip your numbers over.
Yeah.
So you end up getting something slightly smaller than your Ka value rather than something slightly bigger than your Ka value.
Yeah.
Right? You
Okay.
did. So
Yeah.
like the problem was here in this last step, you
Is the
did
acid
HA over A
dissociation
minus instead of A. And you had everything correct. It was just when you were copying your numbers down from your equilibrium into this, you
Yeah.
flipped them.
Yeah. Okay.
Right? And that's where having that kind of mindset of it's a really easy, really common mistake to make.
Mm-hmm.
Which is where having that mindset of where am I on my titration curve? What do I expect? Will save you a lot of points on quizzes and exams where you're like, whoa, this number doesn't make sense.
Yeah.
I was expecting something slightly bigger than my pKa, not something slightly smaller than my pKa.
Oh, because you did PKA. Duh,
So I checked your
buddy.
pKa.
Yeah.
pKa was 4. I was expecting something a little bit bigger than 4.
That's why you asked for what the Ka was.
Yeah.
Okay.
And you got something a little bit smaller than 4. So I was like, ah. And I should have realized right away that it was the mirror image smaller
Okay.
from how much bigger it was going to be. I got to the point where I was like, I have the code wrong. This is like, I did this wrong.
No, I
It's
knew
like,
it was
no,
something
no.
I like. Yeah. I was,
Yeah. So
Okay,
there you
thank
go. Really common mistake, really important thing to keep an eye out for. I'm going to go ahead and end the recording for today. We're almost out of time, so I'll upload it now.